Hey everybody. So today we're going to switch gears and go back to some concrete stuff that involves matrices. Remember that when we learned about invertible matrices, we saw that a 2 by 2 matrix with entries A, B, C, D is invertible if and only if AD minus BC is not equal to 0. You may have wondered at the time, is there something similar for larger matrices? And the answer is yes. If A is an n by n matrix, then there is a number that you can calculate called the determinant of A, and where A is invertible if and only if the determinant of A is not 0. So what is the determinant? How do you calculate it? Before we get into that, it might help to get a better sense of what is going on in the 2 by 2 case. So let's start just by defining the determinant in the 2 by 2 case to be AD minus BC. So to get an idea of what the 2 by 2 determinant means, let's look at the matrix A as a transformation. So on the domain side, we can look at the standard basis vectors, E1 and E2, and we know that when we multiply A times E1, we get the first column of A, and when we multiply A times E2, we get the second column of A. So the image vectors are AC and BD. And then those two vectors determine a nice little parallelogram. So here's a question. What's the area of that parallelogram? It's not something where you can just look at it and see what the answer is, but it's actually not too hard to calculate. The way to do it is to remember that that fourth vertex of the parallelogram is the sum of the two vectors, A plus B, C plus D. And then you can use that point to create a rectangle that the parallelogram is inside of. Here's a bigger picture showing the situation where we have the parallelogram sitting inside of a rectangle. And then it will be helpful to drop horizontal and vertical lines from the vertices of the parallelogram so that you can see some right triangles starting to appear. And then, because we know the coordinates of all of the vertices of this parallelogram, we can actually say what all of the side lengths are for the edges in this picture. And so what this means is that we can calculate the area of the parallelogram by taking the area of the big rectangle and subtracting the areas of the triangles and smaller rectangles. So the big rectangle has width A plus B and height C plus D. So its area is A plus B times C plus D. And so then from that big rectangle, we can get the parallelogram by cutting out some stuff. And so one thing we're going to cut out is those little rectangles in the corners. And those rectangles have area B times C, but there's two of them. So we'll subtract 2 times BC. Then the triangles that are on top and bottom have base A and height C. So each of them has area A times C over 2. But since there's two of them, the total area is just A times C. And then there's the triangles on the left and the right, which have base D and height B. And again, there's two of them, so the total area is B times D. So putting it all together, we've got A plus B times C plus D minus 2BC minus AC minus BD. And when you expand out the parentheses, you get some terms that you can cancel. And when you cancel and simplify, what you're left with is AD minus BC. That's the area of the parallelogram. Now, when you use a picture to calculate something like what I just did, you have to worry about whether there was something special about the picture. And maybe the result would change if you drew the picture in a different way. For example, I drew my vectors in the first quadrant. What if they were in other quadrants? So you have to check all the different cases and make sure that you still get the same result. In this case, you do mostly get the same result, except there is one thing that can change. And that's that AD minus BC can be negative, but of course the area of the parallelogram has to be positive. So the true result is that the area of the parallelogram is the absolute value of AD minus BC. So I think it's helpful to think of this identity in terms of transformations. On the domain side, you have the unit square, which has area 1. And then the image is a parallelogram, which, according to the result we just discussed, has area equal to the absolute value of the determinant of A. It's helpful to think of the determinant as a scaling factor, where the area of the image, which is the parallelogram, is equal to the area of the region in the domain, which is the square, times the absolute value of the determinant. Now what's interesting is that for linear transformations, this scaling principle is true more generally. And here's what I mean by that. The two vectors e1 and e2 don't just determine that one square, but they actually determine the whole grid of squares that covers the plane. Now let's say we have some region in the plane. What do we actually mean when we talk about the area of that region? The area is the number of squares that the region covers, obviously counting those little fractional pieces of squares as fractional pieces of area. That is the definition of area. The units of area are square units of length. And so area really is measured in terms of numbers of unit squares. Now, on the image side, the two vectors will determine a grid of parallelograms. And the image of that blue region will cover those parallelograms in exactly the same way that the original image covered the squares in the domain. So the number of parallelograms covered by the region in the image is equal to the number of squares covered by the image in the domain. And since each parallelogram has area equal to the absolute value of the determinant of A, we get this result, that the area of the image is equal to the area of the region in the domain times the absolute value times the determinant of A. So now, suppose you have two 2x2 matrices, A and B. We know that when you multiply A times B, then you get the same transformation that you would get if you transformed by B first and then transformed by A. And this picture sort of looks like a cute smiley face, so that's nice too. So now let's suppose that we start with the unit square on the far left. Its area is equal to 1. Well, we know that that unit square is going to get transformed by B into a parallelogram, and that parallelogram will have area equal to the absolute value of the determinant of B. Well, then if we take that parallelogram and transform by A, we'll get another parallelogram, and its area will be equal to the area of the middle parallelogram scaled by the absolute value of the determinant of A. So in other words, the area is the absolute value of the determinant of A times the absolute value of the determinant of B. But on the other hand, this is the parallelogram that you get when you just transform the unit square by AB. So looking at it that way, we would say that the area of the parallelogram is the determinant of AB. Both of these things are true, so we can conclude that the absolute value of the determinant of AB is equal to the absolute value of the determinant of A times the absolute value of the determinant of B. So this is kind of cool, but we can do even better than this. I'm of the general philosophy that anytime you have a formula that involves absolute values, there probably is a better formula that contains an explanation for what the sign is. In this case, to get that better formula, we need to use the concept of signed area. Now this is something that you've seen before in calculus. In calculus, you learn that integrals compute area under the curve. But that's not exactly true because area below the x-axis is counted negatively. So there's a sign associated to the area. But where does that sign come from? Why is it there? Okay, so the quantity inside the integral is f of x times dx. Now the dx can be thought of as an infinitesimal vector that's pointing to the right along the x-axis. It's actually a limit of delta x's where delta x is an actual vector that's pointing to the right along the x-axis. And then the f of x can be thought of as a vector that points in the vertical direction. Now let's compare this to what happens when you have a positive function. You've got your dx pointing to the right, and then your f of x is pointing in the vertical direction. But you'll notice that the relationship between the two vectors is different in the different pictures. In the case where the integral is positive, you go from dx to f of x by rotating 90 degrees in the counterclockwise direction. Whereas in the case where the integral is negative, you go from dx to f of x by rotating 90 degrees in the clockwise direction. That difference between counterclockwise and clockwise is a good way of understanding the difference between the positive signed area and the negative signed area. So there's something similar that happens with linear transformations. If you look at E1 and E2, the square they form has the relationship that you get to E2 by rotating counterclockwise from E1. If you look at the image of E1 and E2, they may not form a right angle anymore, but you can still ask whether you're going clockwise or counterclockwise in going from the image of E1 to the image of E2. In the picture that I drew here, you're going clockwise. Whereas in a situation like this, where the relationship from the image of E1 to the image of E2 is counterclockwise, then the determinant of A would be positive. So I think it's helpful to think of the negative determinant as telling you that the transformation involves a flip. And to illustrate what I mean by that, there's a demonstration that I want you to do right now. Get a sheet of paper and draw a counterclockwise arrow on it with a marker or something that's dark enough that you can see it on the other side. And then flip the paper over. What you'll notice is that when you flip it over and look at it from the other side, the arrow becomes clockwise. And now, this is going to feel like a little bit of a leap, but bear with me. We have enough information to know that the equation we had earlier about the determinant of A times B is still true if we just remove the absolute value signs. In other words, the determinant of A times B is the determinant of A times the determinant of B. And the reason for that is, well, we already know the absolute values are the same, and so we just need to explain the positive and the negative. And that just comes down to thinking about how flipping and non-flipping compose with each other. If A doesn't have a flip and B doesn't have a flip, then A times B won't have a flip. And in this equation, that shows up as positive times positive is positive. If A involves a flip, but B doesn't involve a flip, then the composition will involve a flip. And that shows up in the equation as positive times negative is negative. And if both A and B involve a flip, then when you compose them, you get something that's not a flip. And that shows up in the equation as negative times negative is positive. And so the signs work out perfectly, and the equation is true. So let's look at a few basic examples. And of course, the most basic example is the identity matrix. Now remember, we can always calculate the determinants using the AD minus BC formula, and if we do that in this case, we'll get 1. But we can also see that fact in the transformation. As a transformation, the identity matrix just gives you back the same vector that you started with. And so the image of the unit square is just the unit square again, with the same counterclockwise relationship, and so the determinant is 1. Next, let's look at this matrix 1k01. If you use the AD minus BC formula, you'll get 1 times 1 minus k times 0, that's 1. Now let's look at this from the point of view of a transformation. If you multiply this matrix times E1, you get E1 again. But if you multiply by E2, then you get K1. But you'll notice that no matter what K is, the parallelogram that you get in the image has base 1 and height 1, and so its area is 1. And it has the correct counterclockwise relationship to have a positive determinant. And so it makes sense that the determinant is 1. A similar thing happens with 1, 0, K1, and I'll let you draw the picture for that. All right, the next example we'll look at is K0, 0, 1. With that, when you calculate the determinant, you get K. As a transformation, this matrix sends E1 to K0, and E2 goes to E2 again. And so the image is a rectangle with base K and height 1, so the area is K. And you have the correct counterclockwise relationship, and so you get the determinant of K. Or, at least that's what happens when K is positive. If K is negative, then the picture has the image of E1 pointing to the left, and you have a clockwise relationship. But that actually makes sense because, in this case, K is negative, and so the determinant being K agrees with the fact that the determinant should be negative. So either way, it's correct that the determinant is K. So similar to that is 1, 0, 0, K, which also has determinant K, and I'll let you draw the picture for that. And then finally, the last example that I'll do here is 0, 1, 1, 0, whose determinant is minus 1. As a transformation, this matrix swaps E1 and E2. And so you still have the unit square, which has area 1, but there's a flip, so the determinant is minus 1. Now, you may have noticed that this list of examples is a little bit idiosyncratic, and the reason is that I was doing something on purpose here. This list includes all of the 2x2 elementary matrices. And I claim that knowing what happens with all of the elementary matrices, together with knowing what happens when you multiply matrices, gives you another way of understanding how determinants work. In particular, it gives us a way to compute the determinant using row operations. I'll illustrate this with an example. Let's suppose we want to use row operations to compute the determinant of 1, 3, 4, 6. Basically, the idea is to do Gauss-Jordan elimination, but keep track of how the determinant changes at every step. In this case, the first step would be to subtract 4 times row 1 from row 2. But remember that doing a row operation is the same thing as multiplying by an elementary matrix. In this case, the elementary matrix is 1, 0, minus 4, 1. And so there's an equation we can write down that corresponds to this step, that the elementary matrix times the original matrix is equal to the resulting matrix. And then we can take the determinant of both sides and get an equation involving determinants. But this elementary matrix has determinant 1. And as a result, we can say that the determinant of 1, 3, 4, 6 is equal to the determinant of 1, 3, 0, minus 6. And so what we just saw illustrates a general principle, which is that adding or subtracting one row from another doesn't change the determinant, because those elementary matrices have determinant 1. Okay, so probably the next step in the Gauss-Jordan elimination is to multiply row 2 by minus 1/6. Now this elementary matrix has determinant minus 1/6, and so at this step of the process, the determinant will change by a factor of minus 1/6. And this illustrates a general principle that multiplying a row by k changes the determinant by a factor of k. So if we want to write down an equation that relates the determinants at this step, one way to do that is to introduce a factor that cancels out the effect of the row operation. And so we would get minus 6 times the determinant of 1, 3, 0, 1. The idea is that minus 6 cancels out the minus 1/6 that comes from doing the row operation. And then the next step of Gauss-Jordan elimination is to subtract 3 times row 2 from row 1. And as we saw earlier, that's an operation that doesn't change the determinant. And so we can add that to the equation without any new factors. And now we have the identity matrix, and we know that the determinant of the identity matrix is 1. And so we get the result minus 6. Okay, now this might look like a lot of work, but part of why there's so much on the slide right now is because I needed to explain to you why everything works. Once you understand why it works, then the calculation you need to do is just the calculation involving the determinants. So that's not so bad. But then you still might say, yeah, but that's more work than calculating 1 times 6 minus 3 times 4. And that's true. The reason that we're doing this is because this way of thinking about the determinant points the way toward what the definition should be for higher dimensional matrices. And so we'll use this later to figure out how to even define the determinant of a 3x3 or a 4x4 matrix. Okay, now before I end this, there's one more thing I needed to say, because there was one type of row operation that we didn't use in this example, and so I wanted to give you the rule for that. And that's swapping 2 rows. We saw earlier that the elementary matrix that corresponds to swapping the 2 rows has determinant minus 1, and that means that swapping 2 rows would change the determinant by a factor of minus 1. And so if in the course of doing your Gauss-Jordan elimination you need to swap 2 rows, you would account for that by introducing another factor of minus 1 to cancel the factor of minus 1 that you get from swapping the 2 rows.